Balanced flows denote the current network N of P by simply N. We will assume that the network N satisfies the invariant, i.e. S and A union B union T is a mean cut in N. Given a feasible flow F in N, let R of F denote the residual graph with respect to F. Define the surplus of buyer I, gamma I of N F to be the residual capacity of the age I T with respect to flow F in network N, i.e. EI minus the flow sent through the age I T. The surplus vector is defined to be gamma of NF equals to the tuple gamma 1 of NF, gamma 2 of NF, and so on until gamma N of NF. Let the norm V denote the L2 norm of a vector V. A balanced flow in network N is a flow that minimizes the norm of gamma of NF. A balanced flow must be a max flow in N because augmenting a given flow can only lead to a decrease in the L2 norm of the surplus vector. Lemma 5.4. All balanced flows in N have the same surplus vector. Proof. It is easy to see that if gamma 1 and gamma 2 are the surplus vectors with respect to the two flows F1 and F2, then gamma 1 plus gamma 2 over 2 is the surplus vector with respect to the flow F1 plus F2 over 2. Since the set of feasible flows in N is a convex region, so is the set of all feasible surplus vectors. Since a balanced flow minimizes a strictly concave function of the surplus vector, the optimal surplus vector must be unique. The following property of balanced flows will be used critically in the algorithm. Property 1. If gamma j of n of f, which is less than gamma I of n f, then there is no path from node j to node I in R of f minus the set st. Theorem 5.5. A maximum flow in N is balanced if and only if it satisfies property 1. Proof. Let f be a balanced flow and let gamma I of n f is greater than gamma j of n f for some I j in B. Suppose, for the sake of a contradiction, there is a path from j to I in R of f minus the set of S entity. In N, the only edge out of J is the edge JT. Since the path in R of f from J to I must start with a positive capacity H which is different from H JT by flow conservation, the capacity of Tj must be positive in R of f. Since our gamma I of NF is greater than 0, the edge IT has a positive capacity in R of f. Now the edge Tj and IT concatenated with the path from J to I gives us a cycle with a positive residual capacity in R of f. See figure 5.3. Sending a circulation of positive value along this cycle result in another max flow in which the residual capacity of J is slightly larger and that of I is slightly smaller, i.e. the flow is more balanced. This contradicts the fact that F is a balanced flow. To prove the other direction, first observe that the L2 norm of the surplus vector of a max flow F satisfying property 1 is locally optimum with respect to changes in pairs of components of the surplus vector. This is so because any circulation in R of f can only send flow from a high surplus buyer to a low surplus buyer, resulting in a less balanced flow. Now, since L2 norm is a strictly concave function, any locally optimal solution is also globally optimal. Hence, a max flow F satisfying property 1 must be a balanced flow.